I'm happy to introduce our last speaker. It's going to be Sela, who will speak about mirror symmetry for open Gromov-Witten invariants of Fano manifolds.
So thank you. So I'll start with talking about what open Gromov-Witten invariants are. So let X be a symplectic manifold, and L is a Lagrangian submanifold in X. Beta is a second relative homology class, and K is a non-negative integer. And by OGW beta K of L, we denote the number of geomorphic disks in X with a boundary on L, such that the boundary represents the class beta and it intersects K generic points on L. And to these numbers we call open Gromov-Witten invariants. And maybe just a remark that in order this counting to be actually well defined, we need to add some correction terms in here that coming from boundary quotients and sphere countings. But for our purposes in this talk, it will be suffice us to consider this as a definition. And now let's assume that X is also a Fano manifold. So its mirror is a Landau-Ginzburg model, YW, where Y is an open Calabi-Yau manifold and W is a holomorphic function on Y. And Lagrangian submanifolds in X, which can be considered as objects in the Fourier category of X, under mirror symmetry should correspond to algebraic objects called matrix factorizations, which are objects in the matrix factorization category, which is associated to this Landau-Ginzburg model. These notions will be defined in a few more moments. And to Lagrangian submanifolds, we can associate open Gromov-Witten invariants. And our goal in this talk is to define invariants of matrix factorizations that we call numerical invariants, such that they should correspond to open Gromov-Witten invariants in a way we will discuss in the end of the talk. And the definition of these numerical invariants will be depend, as we will see later, on a solution to an equation called Maurer-Cartan. And the way to find such a solution is by obtaining approximations using abstraction theory that will eventually converge to such a solution to this equation. And in order to be able to define such approximations, we will need to use norms in our setting. So what we're going to do is to define these two notions by using a non-Archimedean setting. So Banach-Landau-Ginzburg model is the following triple, where R together with the norm nu R is a unital Z-graded Banach ring. S together with the norm nu S is a unital finitely generated Z-graded Banach R algebra. And W is an element in S, which is called the superpotential. And this Banach-Landau-Ginzburg model gives rise to a category called Banach matrix factorization category, which is the following product of these categories indexed by elements in the Banach ring R. And these categories are defined as follows. So objects, which are called matrix factorizations, are the following triples, where M together with the norm nu M is a finitely generated Z-graded projective Banach S model. And this model is equipped with an endomorphism dm, such that its square is the superpotential minus this little w times the identity of M. And this endomorphism preserves the norm in the following way. And for our purposes in this talk, it will be suffices to consider matrix factorization just as S models. And morphisms in this category are bounded S model homomorphisms between M1 and M2, bounded with respect to a norm induced by the norms on M1 and M2. And this category is equipped with a differential denoted by delta, given by the following formula. And the composition between morphisms in the category is just a composition of S-model homomorphisms. And this makes the Banach matrix factorization category into a DG category. And an example to these constructions that coming from toric geometry is the following. So assume we have a Delzant polytope, so we can associate it a symplectic toric manifold X triangle. And by using the combinatorial data of this polytope, we can construct a Banach-Fano-Gisburg model associated to this toric manifold. And this gives rise to a Banach matrix factorization category. And in addition, we can construct, by using family flow theory, matrix factorization, an object in the category that is associated to the real part of the toric manifold, which is a Lagrangian submanifold in the toric manifold. So before we define the numerical invariants, a few definitions before. So the first is of the cyclic complex of the Banach matrix factorization category. So its degree L part is defined as follows. So it's a direct sum of tensor products of Hom complexes in the category, taking the sum over a collection of length L of objects in the category, and we modding out by some action of rotations on this tensor product. And this cyclic complex is equipped with a differential given by this formula. It will not be important. It won't be important for this talk, but the differential is determined by the differential of the category and the composition of the morphisms in the category. And if we consider this cyclic complex and we modding out by the cyclic complex of the Banach ring R, which is a subcomplex generated by the identities, by tensor products of the identities, then we obtain a complex called the reduced cyclic complex. And this reduced cyclic complex we equipped with a functional, which we denote by theta, such that the composition of this functional with the differential on the category, on the complex, sorry, gives 0, and such that theta is compatible with the norms on the Hom complexes of the category. And to such a functional we call contractive infinity trace. And an object M, which we call also a matrix factorization, we call non-degenerate if the following pairing induced by the contractive infinity trace theta, given by this, is non-degenerate, where and M0 is our notation for the endomorphisms in M with non-negative norm, modding out by those with positive norm, and similarly, R0 is the elements in R with non-negative norm, modding out by those with positive norm. And last definition for our definition to the numerical invariants. So assume we have B in this ring. This is the ring of power series with a formal variable S and coefficients in the endomorphisms of M. And C is in this power series with coefficients in the Banach ring R. And assume these two elements satisfying the following equation called Maurer-Cartan equation. So the differential of B minus its square gives C times the identity of the matrix factorization M. Then B and C gives rise to a co-cycle in the reduced cyclic complex, denoted by X tilde of B. And basically this element is the exponent of B plus some correction terms, making this sum to a closed element in this complex. And maybe just give a feeling of how this co-cycle looks like. It won't be important for us, but still. So it's the exponent of b, this is the first sum, plus infinite sums of many tensor products involving b, the identity of m, and c. Okay, and if we have a matrix factorization m, we call it a spherical object if the cohomology of n and m0 isomorphic to the cohomology of the n-dimensional sphere with a coefficient in R0, where this is the reminder of what m0 and R0 are. And our main theorem is the following. So suppose that the Banach matrix factorization category is equipped with a contractive infinity trace theta, and let M be a matrix factorization which is spherical and non-degenerate. Then there exists a unique C such that there exists an element B such that they both are satisfying these conditions. So the first one, they satisfying Maurer-Cartan equation, and the second condition is sort of a normalizing condition of this co-cycle with respect to the contractive infinity trace. And it is normalized to be the formal variable S. And now we are heading to the definition of the numerical invariants of matrix factorizations. So now instead of considering an arbitrary Banach ring R, we work with a specific choice of R being this Novikov ring. So it's the ring of power series with a formal variable T, where the powers live in an abelian group G, and the norm on R is determined by a homomorphism H on G. And assume, as before, that we have elements B and C that satisfy Maurer-Cartan equation and this normalizing condition. So since C lives in this ring, it can be written in the following way. And to these numbers, to these real coefficients, the coefficients of t the power of d, s in the power of k over k factorial, to these real numbers we call the numerical invariants that are associated to the matrix factorization M. And by previous theorem, we call that if M is spherical and non-degenerate, then there exists B and C satisfying these two conditions. So in this case, M is spherical and non-degenerate, we can define the numerical invariants associated to this object. And recall that we can construct Banach matrix factorization category that is associated to toric manifolds. So we are now focusing on this case. So the following conjecture says that for each Dilzant polytope, the Banach matrix factorization category associated to the toric manifold corresponds to this Dilzant polytope is equipped with a contractive infinity trace such that every object in this category is not degenerate. And the second conjecture asserts that, well, recall that this is our notation to the matrix factorization associated to the real part of the Fano toric manifold. So if the real part is spherical, meaning that its cohomology isomorphic to the cohomology of the n-dimensional sphere, then the matrix factorization associated to it is also a spherical object. And an example where these conjectures hold, or at least parts of these conjectures hold, is in the case that our toric manifold is a CPN. So the Dilzant polytope is the n-dimensional simplex, and we consider the cases where n is odd. So the Banach matrix factorization category associated to CPN is equipped with a contractive infinity trace theta. So this an example for the formula of what theta looks like. This giant and scary formula defined by Shkelarov, which showed that this functional is closed, meaning that the composition of this functional with the differential is 0, but we can also show that this functional is compatible with the norms on the Hom complexes of the category. And basically, in order to compute things with this functional, you need to take many sums of some residues of some functions, but we can ignore for this. So the Banach matrix factorization category associated to CPN is equipped with such contractive infinity trace. And in addition, the matrix factorization that is associated to RPN. RPN is the real part of CPN. So this matrix factorization is spherical and non-degenerate. And by previous theorem, it means that this matrix factorization admits numerical invariants. And the following conjecture aims to show the correspondence between open Gromov-Witten invariants and numerical invariants, at least in the case of Toric Fano manifolds. So our manifold is Toric Fano. And we assume that its real part is spherical. Then the numerical invariants of the matrix factorization associated to this real part supposed to reproduce open Gromov-Witten invariants of this real part. And if to be more precise, what does it mean? So it means that there exists a homomorphism from this second relative homology into G, such that this formula holds. That's supposed to show the connection between the numerical invariants and the open Gromov-Witten invariants. And an examples where this conjecture holds. So it's in the case also of CPN. So the real part is RPN, and in the case where n equals 1, then the numerical invariants of the matrix factorization associated to RP1 reproduce the open Gromov-Witten invariants. And in the case where n equals 3, then we can compute the numerical invariants of the matrix factorization associated to RP3. In this column, you can see the numerical invariants of lower degree. And in this column, the open Gromov-Witten invariants of RP3 of lower degree. And we can see that up to sign, they agree. And in this column, just to show the effort that it's needed in order to compute these invariants. So if you recall that theta is given by many sums of residues of some function, so these are the numbers of residues are needed to compute in order to obtain these numbers. So these two examples were the conjecture that aims to show the correspondence between open Gromov-Witten invariants and numerical invariants satisfied. And that's all. Thanks for listening.
Thank you very much. Any questions?
Yes, maybe just to clarify the correspondence statement, are you saying that you can recover? Yes. So no interior constraints on the right-hand side and on the left.
Yeah, only boundary constraints.
Only boundary constraints, and case starts with 1 because that's what Maurer-Cartan would see.
Yeah.
Right, I see. So it looks like the computing procedure is very long. So do you just show this table because this is as far as your program went, or do you have other examples maybe?
Yeah. The next non-vanishing invariance is pretty hard to compute. Hopefully in the next few weeks we will be able to compute it. Yeah.
I see. What would be the next example you'd like to test?
Like what other manifolds?
Yeah.
So CP3, blow up of CP3 at one point, it seems
At a real point.
yeah, at one point. It seems, well, we add some computations concerning this manifold.
Mhm.
But now this is actually a work in progress to find other Lagrangian submanifolds inside CP3 or maybe in CPN in general.
But you still want them to be both spherical and the real locus of an
Yeah, they
evolution.
have to be spherical. Yeah.
And optimally something where the open invariants maybe are already computed.
Sorry?
Optimally also an example where the open invariants are computed.
Yeah, to convert it into open invariant and open Gromov-Witten invariants that
Yeah.
computed.
That's
yes.
not a very big pool, but okay, sounds good. There are some. Okay. Thank you.
Sure.
Any other question? There's a comment by Claude. Thank you for the 3 very nice talks. Unfortunately, the clap button has disappeared on my Zoom. Okay.
Thank you.
Okay, so I don't know if there are no other questions or comments, then let's thank May again. Thank you.